Good morning. We continue our lecture on solidification of binary alloys. Under this, we have primarily looked at several binary systems like isomorphous system. We also looked at the difference between an ideal and real solid solutions. We looked at free energy composition diagram of isomorphous system. We talked about solubility limit and three phase equilibrium and considered several three phase reactions that are possible in a binary system like eutectic, peritectic, monotectic. We also looked at solid state transformation, say like not only precipitation, but also solid phase transformation, solid state transformation involving reactions where three phases are involved like eutectoid, peritectoid, monotectoid, etc. Then we looked at complex binary diagram, we looked at several examples, but so far we have not looked at effect of non-equilibrium cooling, and today we will look at primarily on effect of non-equilibrium cooling. But before that, let us look at some of the calculations that we did with certain assumptions about phase diagrams. Now, in binary phase diagram, it is basically a graphical representation of phase compositions and their amounts at a given temperature and pressure, and usually this pressure is 1 atmosphere, and the system is assumed to be under equilibrium at every step, and it is a useful tool for quantitative evaluation of alloy behavior, and we looked at certain examples, and these are the things which we have covered. We also looked at how allotropic transformation is represented in a phase diagram. Now, we used principle of thermodynamics, because thermodynamics is the basic science which deals with equilibrium, and using certain thermodynamic data, we calculated say phase diagram for an isomorphous system. And if we take that example for nickel and chromium, we did it I think in one of the classes with arbitrary values for A and B, but if you substitute for nickel and copper, then its melting points are known. This is the melting point of nickel, this is the melting point of copper, this is the enthalpy per mole of melting, and this is the enthalpy change during melting or latent heat of melting for copper, and this is the universal gas constant R. And we make an assumption that nickel and copper form ideal solution in both liquid and solid state. And using this, we calculated the phase diagrams, and here it looks like this. This black line here, which represents the calculated liquid S line. Similarly, this violet one, this line, it represents calculated or predicted solid S line, and we have superimposed here the experimentally obtained liquid S and solid S line from handbook data, and you look at say with these assumptions we are not very far away, although there are little deviations, but near these both these ends, or this is we can say that this is nearly follows an ideal solid solution, an ideal solution. I mean nickel and copper, if we assume that in liquid state they form ideal solution in both liquid and solid state, this assumption is not far away from reality. And we also looked at an extreme case of liquid solid immiscibility. Say we assume that for bismuth and cadmium, if you assume that in the liquid state they form ideal solution, and in solid state they are totally immiscible. That means, when solidification takes place, if it is in the bismuth end, you have primary bismuth precipitating out, and you have you are on the cadmium end, then pure cadmium precipitates out when the solidification begins, and this forms an eutectic system. And with this assumption that they are totally immiscible in solid state, we did calculate the phase diagram using the concept of thermodynamic equilibrium, and here these points, they represent the predicted values, and if you extend those, you also get, say, eutectic is around somewhere here. This is the eutectic temperature around 408 degree Kelvin, and the eutectic composition comes around 0.56, and on this we have superimposed the experimental or actual values from handbooks, and if you do that, you find you are not very far off. So, that means this type of, by using thermodynamic model, it is possible to calculate phase diagram, and in fact, in binary system it is easy, and later on as we proceed, we will find this is applicable in general. It can be used even in ternary and quaternary systems as well. Now, let us look at the concept of an ideal solution. What is an ideal solution? Now, in ideal solution is primarily what we look at, say this is the free energy composition diagram, which is shown over here for an ideal solution. So, this is the axis for free energy, and this is the atom fraction B. This end is pure A. This is the standard state, say A has a free energy when it is pure, B has a free energy when it is pure, and if it is a mechanical mixture, they do not dissolve in each other, then this will be the line which will give you the free energy of the mixture. But in reality, say they mix, and they mix in all proportion, in that case that free energy goes down, and somewhere in between you will have maximum stability or the lowest free energy. Now, here then you can say that free energy of mixing can be written as this plus that we say that this is the general expression for free energy of mixing, and these are in the pure form if they mix, but if they go in solution, this will be the change. So, that means from this it goes down, and here this activity is always will be less than 1. So, this will be negative. So, this will be lower than this line. Now, an ideal solution is one where activity is equal to atom fraction. So, activity of A in the solution equal to N A activity, and similarly activity of B is equal to atom fraction B, and there is no heat of mixing. That means, if you mix the two, there is no temperature change. That means, so no heat evolved or heat absorbed. So, delta H or enthalpy of mixing is 0. So, therefore, this term actually represents that entropy contribution, and this is called an entropy of mixing, and which is equal to I think there is a mistake here. It should be T, it should be R. So, this is, so delta H by T is actually entropy of mixing. Entropy of mixing is actually entropy of mixing. Entropy is the dimension is heat. So, we can write that delta H mix free energy of mixing equal to delta H mixing minus T delta S mixing. Now, here we assume that this is equal to 0. So, therefore, delta S mixing equal to minus R A N B So, this is the correct expression for entropy of mixing. So, what you can see, this atom fraction, this will always be less than 1. So, whenever you are mixing, so what is happening? The disorder increases. So, this is positive. So, delta S mixing is always greater than 0. Now, if you plot the ideal activity of ideal solution, if you plot the activity against atom fraction, say in that case the activity equal to atom fraction is given by this line at 45 degrees. So, this is the case for ideal solution, and here this is the activity, and in reality we usually have some deviations, either a positive deviation, that is activity is greater than atom fraction and it describes a path like this, and it can also be the other way, the activity of B is less than the atom fraction B, and it follows this type of path. So, actually what is happening here in this part, you have activity is greater than N B. With any point you take, this is N B, this is the activity. So, here this part, bottom part, you have activity of B is less than N B. Now, activity you can say that it actually gives you an approximate composition, or you can say local concentration of B atom around B. So, if activity of B is greater than N B, that means there are more than expected number of B atom around B, whereas here there is less than expected number of B atom around B. This is what it means physically. In the same way, you can also plot activity of A in this axis and atom fraction N here. So, in that case atom fraction here it is 0, and here the ideal solution curve is like this. Now, whenever there is a deviation, you can still make approximation at two ends. So, one is the approximation in this end, where you can say that activity of B is linearly proportional. So, there is an activity coefficient N B, and here this gamma B is greater than 1, and this is called activity coefficient. So, this part follows like this, whereas in the other end this part it is nearly approaching the ideal behavior. So, that means this part it is N B. So, this means when N B is approaching 1, this is the behavior, and where N B is approaching 0, then this is the behavior. So, and this is called, so distinctly we can divide this zone into two parts. One we can say where it follows ideal behavior, then we say that it follows Raoult's law, and in the dilute solution regime it follows Henry's law. So, with these assumptions also you can make further corrections to the phase diagram that you calculate, and it is possible, I mean vice versa, either you can calculate the activity coefficient from the phase diagram which is experimentally determined, or if these activity coefficients they are known, you can calculate the phase diagram. And let us consider a case where there is some deviation from ideality. So, here we have taken up a case of a regular solution. Now, what is a regular solution? This is the free and expression, general expression for free energy of mixing. You have an enthalpy term, you have an entropy term, T delta S is the entropy. And here for a regular solution, assumption is the entropy of mixing is same as entropy of mixing in ideal solution. This is an ideal solution, there is a mistake here, correct, ideal solution. And you say, and let us assume that in this case this enthalpy of mixing is not 0, either it is positive or negative, it is either endothermic or exothermic. And in that case, how do you calculate this enthalpy of mixing? Now, enthalpy, we can say that usually whenever there is a bond formation, so energy which is required to break the bond. So, in solid there is a bond, say there will be two kinds of bond. If it is a binary solution of A and B, there will be A type of bond, there will be some BB type of bond, and there will be some AB type of bond. And enthalpy of mixing is equal to the total bond energy, where in AA represents number of AA bond, and this is the energy of each AA bond. So, this is how you can write the entire that enthalpy of mixing. Now, how is it possible to calculate this theoretically? Let us see how this is done. Now, when you form bond, say here is a 2D representation of a bond formation. This is an atom A, let us say, and it has 4 bonds. In that case, here there is number of bond formation is 0. Now, here if bond forms with similar atom, which is shown over here, so few of these bond forms. So, here number of bond, this is 1, 2, 3, 4 bond forms, and these are yet to form bond. But if you go on adding more and more number of atoms, you will find that number of these bonds increases, and it increases much more than the bonds which are free. And this is the way, if you can go on adding, finally you will find, if it is possible to calculate the number of bond if you mix say certain number of A atoms. Let us say that Z is the coordination number of nearest neighbor. So, here we can say this atom can have 4 nearest neighbor. Consider this is 1, 2, 3, 4. So, this is the nearest coordination number, or we can say number of nearest neighbor. Then how do you calculate NAA, that is number of NAA atoms? Then you can find out if you have in a number of A atom, each has coordination number Z. So, Z times this, there will be so many bonds, but when actually bond formation takes place here, this is counted twice. If you count like this, so number of AA bond will be this over 2. So, similarly, you can find number of BB bond, this will be Z times NB over 2. And now, if you mix these together, then how will you find out the total number of bonds? I think I will leave it to you, and in fact, what can be shown that this is how you will calculate this number of AB bonds. So, I think this should be AB. And now, with this, let us try to find out how do we calculate that enthalpy of mixing. Now, so in this case what we say that when you mix, then you have total number of atom is Na plus Nb, and if we consider that this is the 1 mole of solution, then we can say that N is the Avogadro number. Then we have that atom fraction Na. So, this will be Na over this total number of atoms. Make this smaller n. Then atom fraction B will be Nb over Na plus Nb. So, this, and then when they are not mixed, so before mixing there will be total bond energy, which you can find out that if there is an Avogadro number of atom, out of this if you multiply, this is the number of A atoms, you multiply this by the coordination number, divide by 2. So, this is the number of bonds of type AA, and this energy is AA. Similarly, you can do it for BB type of bond. So, this is Nb divided by 2 . Now, when mixing takes place, then what happens? Now, here certain number of AA bond will be replaced by AB bond, and how do you calculate this? Now, this will be Z n by 2. This is the total number of bonds Na. Now, out of this N A fraction is replaced, only is now a type of bond. So, therefore, this will be this. Similarly, you will have the BB type of bond, energy due to BB type of bond will be BB plus there will be Z n Na Nb types . So, this is what is written here. If you, so this is the total energy. Now, when you mix, the net energy change, enthalpy of mixing will therefore be given by E minus E naught. When you do this, and with a little simplification, you will be able to show that enthalpy of mixing is equal to this enthalpy of mixing is equal to Avogadro number times coordination number, then Na Nb, and there is an energy term, and this energy term, this is nothing but the bond AB type of bond formation energy, when AA epsilon BB and we usually represent this as omega Na Nb. Now, look at this term. Now, if the tendency of ordering is more, so if A B, if this is more than this, then epsilon is positive. In that case, this omega, you can say this omega is equal to n z epsilon. So, if omega is this is positive, then omega is greater than 0, whereas if A type of bond is preferred than A B, in that case this is less than 0. Now, when you have this, how does this free energy composition diagram look like? So, this is what has been worked out, the regular solution model. If you substitute this and with a little algebraic simplification, and here what we have done, we have multiplied for this simplification. What we have done is multiplied this by N A plus N B. These are atom fraction A, atom fraction B, and they add up to 1. And then this N B square times N A, this is clubbed with this, then you get this entire expression can be algebraically simplified and written like this. So, you have now two parts. This is the free energy that you can say this is the partial molar free energy of A in the solid solution, this is the partial molar free energy of B in the solid solution, and these two are written like this. So, so what you have is for a regular solution, we get a it is possible, assuming this assumption that nature of bond and how do they form, and from the bond energy, it is possible to derive an expression for activity of specific atom A and B in a regular solution model. So, this is equal to, you can say this is the standard state, then you have omega 1 minus N A square plus R T ln. So, had it been ideal solution, for ideal solution omega equal to 0 for ideal solution. But in this case, this is this. So, therefore, this is equal to, you can write that G A plus R T ln activity of A. So, therefore, one can show that activity A is equal to activity coefficient A times atom fraction, and therefore, gamma A will be one minus. With this, it is now possible to calculate let us say that free energy, enthalpy and entropy of mixing, and they are plotted here, and this is the nature of the plot looks like this. So, when it is gamma is less than 0, this is the type of deviation that you have, whereas if omega is greater than 0, then this is the type of free energy composition diagram you expect. Here both enthalpy and T delta is both in the positive directions and in they add up. So, you get this type of diagram, and using this, now it is possible you can calculate, it is possible to calculate the phase diagrams in cases where you do not have these assumptions are not valid. That means, ideal solution assumptions are not valid. Say suppose you take up a case of say silver and copper. Now, check up its melting point of silver and copper, and they form eutectic with terminal solid solution. So, this is alpha, let us say this is beta. Now, here you take a case at a particular temperature, you try and equate the partial molar free energy or the chemical potential of A in alpha equal to chemical potential A in liquid, and if you equate the two, you can, it is possible, I mean here you can have two kinds of equilibrium, this part B in alpha, B in liquid. So, with these equations and assuming regular solution, it is possible to calculate this and this. Same way you can equate the mu A in beta, equate it to mu A in liquid, equate mu B in beta, this is equal to mu B in liquid. By this you apply this to these 2 points, it is possible to calculate these compositions, and once you do it for different temperatures, you extend and you will get this eutectic temperature. I leave this to you as an exercise, you try it, but and get this thermodynamic, that is latent heat of melting for silver and copper from handbook. You can get this and you can, but here you will find you have to use a little trick to solve, because these equations may not be nonlinear in these compositions, that atom fraction B, and you may need some iteration scheme to find out the solution. And now, let us see, with this I think we have completed more or less the simple binary phase diagrams. Before we proceed further, let us look at, there are certain limitations of phase diagrams which are given here. This phase diagram gives you structural evolution, no doubt, but only when the system is cooled at a very slow rate. This gives no information on the rate of transformation. There is another variety of diagram which is called time temperature transformation diagram or TTT diagram, which provides complementary information, and later on when we look at, we will separately look at this at a later stage. But when you actually make an alloy, there are certain constraints. Say suppose when you make an alloy, what you do, you will melt and you will pour it in a mold. You will pour it in a mold. So, this is the liquid, and now heat will flow through the mold. Now, the way that heat is extracted, that will determine how the structure will form, and we have also seen for solidification to start, some amount of supercooling is necessary. So, in that case, the way the structure forms, it will depend on the way the heat is extracted from the liquid. And let us look this in a little more detail. We will look at it in a little more detail, and now let us see that can we use phase diagram to understand effect of non-equilibrium cooling, and which is shown here. First, let us take up the case of an isomorphous system. Now, in an isomorphous system, the situation is, say you have liquid, and we also know that movement of atom in liquid is much faster, diffusivity is several order of magnitude higher in liquid, and therefore, we can assume make an assumption that liquid composition can change much faster than that in solid. Now, here when the solidification begins, the first solid that solidifies for this particular composition, alloy composition, the composition of the solid will be given by this point. You draw the tie line, horizontal line, it intersects solid as here. So, this is the composition of the first solid that precipitates out. Now, when the temperature comes down, say suppose here, then the next solid which will precipitate out at this temperature must have this composition. Now, what happens to the solid that has solidified earlier, and if we assume that the diffusivity in solid is very small, in that case what we can think, say the first solid which precipitates out here, say maybe this is the first solid, it has certain composition. Say suppose this has 2% B. Now, the next solid that precipitates out surrounding, say now next one, say this is, let us say this is 5% B. Now, if we make as an assumption that diffusivity in solid is extremely small, so this composition will take very long time for it to change. In that case, we can see that the next solid, it is surrounded by each, that as the crystal grows, it is surrounded by solutions which are richer in B, and this is the next one, next layer will be even richer in B. So, let us say this is 10%. So, as you go move from the center of the crystal to the periphery, you will likely to find that composition goes on changing. So, in a way what we can say that the solid composition, so here the first solid which precipitate has this composition, next solid has this, next solid has this, next layer has this, but then the average composition if you try and calculate, it will not be if it were possible to cool it very slowly, it would have followed this line, then it would have moved from here to here. Now, instead of moving here, then we can say the average composition lies somewhere here. So, that means if there is a departure, what will happen? The average composition of the solid will follow a different line. The solid is not able to change its composition very fast as it is expected. Therefore, the average line follows this, and the last liquid which solidifies here, solid, it will have a composition which is richer than even that last solid, will have more B. So, B in last solid will be greater than actual composition, average composition of the alloy, and this phenomena is known as coring. So, that means using the simple concepts and that assumption that even if we can use to some extent to understand the structural change that is likely to take place when there is a departure from equilibrium cooling. And finally, what you will have a code structure, you will have different compositions from center to periphery. So, you will have, so normally if you look at the microstructure, you can see that different composition, they will reach little differently. So, you will get a gradation of contours, so which is basically represents non-uniform composition. Now, same thing you can extend it to eutectic structure. So, eutectic, say suppose here we consider this is a case. what is the non-equilibrium cooling in case of an eutectic system. Now, let us look at this terminal solid solution. Now, here that initial composition that precipitates out when the temperature goes below the liquidus. So, this is A, this line represents pure A, this is pure B, and when this liquidus line temperature goes below this liquidus, the first solid that precipitates out has this composition. As it goes to the next temperature here, the solid precipitating out will have this composition. So, new crystals or new layers of alpha which is forming, they will follow this composition, whereas the older, if you older will not get enough time to change its composition. So, therefore, effectively what will happen, the average composition of the solid will follow a line, a solidus which is different from this, and this is a departure from equilibrium. And ultimately what it may have, when it has reached the eutectic temperature, possibly there may still be some amount of liquid left. So, this is the amount of liquid which is from this point to this point. This is the amount of liquid which remains even when the temperature reaches the eutectic temperature. So, this will now solidify as eutectic, having alpha of this composition and beta of this terminal solubility somewhere here. So, therefore, the structure will look like you will have primary core grains of alpha. Let us say this is alpha, this represents the different composition contours, these lines represent different contours. This is one grain of alpha, this is another grain of alpha, these are contours, composition contours. So, these are alpha, and still there is some amount of liquid which is will solidify as eutectic. So, there will be mixtures of alpha beta. So, normally, so what effect of non-equilibrium cooling in this case is, you can get eutectic even in composition, even in terminal solid solutions, where you will under equilibrium cooling you do not expect any eutectic. So, this is one important departure which is expected if the cooling is not very slow, if the alloy is not cooled at a very slow rate. Now, let us look at a peritectic system. Now, what happens in a peritectic system? Here same concept we can apply in the peritectic system, and let us consider in the peritectic system this alloy. Now, this is the peritectic point. Now, in this peritectic alloy, so that means here this is the alloy composition. Now, the first liquid which precipitates out will have this composition. Now, when it comes here, then its composition of the liquid solid will be this, and the average composition will be this. When it is here, then the new solid which precipitate out has this, and average composition is this. So, here also it follows the solidus, actual solidus, real solidus. This you can say that real solidus, this is ideal case when it is under equilibrium, and here it is real solidus, that is non-equilibrium. Now, it follows in that case what you have now, you have this is where you have come. Now, here your amount of liquid is, there is some amount of liquid here, even here. So, amount of solid at at the peritectic temperature is proportional to this part, amount of liquid is this part. And what happens now, this amount of solid alpha at peritectic temperature, that is liquid will react with that alpha and will give you beta. So, here what is happening, there is coring no doubt. So, that means that primary alpha which has formed, it has a cored structure. Now, when the peritectic reaction takes place, what is happening, that liquid surrounding reacts with alpha at the peritectic composition alpha p. This is the liquid peritectic composition. This will give you beta of that peritectic composition, and this beta will form surrounding this. So, it gets encased. Now, this alpha, if it has to react with a liquid, now it is becomes quite difficult, because it is not in contact with the liquid. So, what is likely to happen? Some amount of primary alpha will get surrounded and retained even in this peritectic alloy, and once that peritectic reaction is complete, then what is happening, this composition, peritectic composition is this, still there is substantial amount of liquid, and here now the liquid now has this composition. Now, this starts changing like this. The liquid composition will follow this path, because the diffusivity in liquid, the movement of atoms in liquid is faster, it is able to change, adjust composition with decreasing temperature, but solid is not able to adjust the temperature, adjust composition with decreasing temperature. So, here also that average composition would follow this line, and ultimately the solidification will be completed somewhere here, that is at temperature much lower than the melting point of B. So, here it is little more complex. So, in case of a peritectic reaction, if there is in any system, if there is a peritectic reaction, you will have primary alpha will get surrounded, primary, this is alpha, get surrounded and retained even in peritectic alloy. Now, let us build upon this. So, that means we can use to some extent equilibrium diagram to understand what will be the nature of the structure, actual structure in a real alloy. So, that means composition, if you cool at a normal rate, composition is not going to be uniform. So, all cast metals, they will have some amount of from point to point composition may vary, and if you want uniform composition, you have to give some heat treatment after solidification, and we will come to it later as well. Now, let us look at the effect of temperature gradient. We talked about solidification in a mold, and when solidification takes place in a mold, the nature of the structure that develops will depend on the way heat is extracted. So, that means if you, and for simplicity, let us take in a real mold, heat may be flowing. In a real mold, if you have like this, heat will be flowing in this direction, different directions. So, therefore, the structure will be, solidification will start from this end as well as this end, and we can assume that here since which is exposed, or if it is covered also, here also that if it is encased in a metallic, on all sides. So, this side also the heat will flow. Similarly, you have to depend on the top how you are maintaining, is it open or is it also in contact with the metallic mold. So, that rate of cooling will be determined on the nature of mold and nature of the surrounding. Let us take a simple case where this is the one part, this is the solid, this portion is liquid, and this is the solid liquid interface, and heat is being extracted from the solid only along this. In that case, if it is a pure metal and we have this type of a gradient. So, this is that interface of a solid and liquid, and the gradient is like this. The heat will flow from higher to lower temperature, from this end to this end. So, that is why here the temperature is lower, and in the liquid is at a higher temperature, and you have a positive gradient here like this. In this case, if it is a pure metal, we will and positive gradient, this will give non-faceted or planar interface. That interface, this plane will try and move like this. Initially it is here, as the temperature goes, it comes here, it comes here, this becomes solid. So, here even if there is a, it tries to say somewhere it tries to go like this, in that case when this solidifies, it will, there will be latent heat which has to be extracted. If it comes this side, it can, that heat can go this way also, it will heat up and melt. So, it will not be stable, this kind of any departure from planar interface will not be stable in the case where you have this type of gradient. But there are certain materials like some inorganics where you know this phase can also be this kind of a faceted like this. Okay. This kind of a faceting can take place in inorganic and some semiconductors. Now, it is also possible to maintain a negative this type of gradient as well, which is little difficult. You can visualize, suppose in a mold, you take a mold and you have supercooled let us say tin. For solidification, it is necessary to have some amount of supercooling. This is supercooled. In this case, it is possible to maintain a temperature gradient. So, it is supercooled, when you pull it and then solidification starts, then temperature goes up. So, here you will have the temperature maybe like this. This is the temperature and this is the temperature, you can say this is the freezing temperature of that metal. So, something like this. So, in this case what is happening, since the temperature nearby area is less, in this case if this is the interface, if there is a deviation like this, this temperature is lower. So, when it solidifies, the heat can flow in this direction as well. So, this is stable. So, in this case you have this type of a tree like structure developing. They are called dendrite, in Greek it means tree like. So, this is called dendrite. So, this type of shape of this primary crystal is also possible, and all this will determine by the thermodynamic characteristic of the material, and there are certain correlations people have found out. And looking at the thermodynamic database, if you find that there is some correlation with entropy change, this entropy over R. So, this is a dimensionless number, entropy over R, and if you try and find out, for most metal it is less than 2. In this case you get planar interface between solid and liquid, and which is represented schematically. Some metalloids like silicon, germanium, bismuth and certain other materials where this is in this range, you get faceted structure, and most inorganics this is much higher, and there you invariably get this kind of faceted structure. And the crystal growth is also depends on the directions, and the growth direction is fastest along this cube direction in FCC and BCC. So, these planes, so when these crystals are growing, so this plane or plane normal, this will be one of these cube directions in FCC, and in hexagonal close pack structure, this is 1 0 1 bar 0. This is the directions or that plane. This is the plane on which the crystal growth takes place. Now, in essence, the flow of heat flow on the has an important effect on that interface movement, and which is represented here. This is the heat conduction through solid, this is the conduction through liquid, and this is the latent heat that comes out when solidification takes place. Rho is the density and R is the rate at which this interface moves. And so, assuming this to be planar, this type of equation can be set up, and we will build upon it. We will see how this affects evolution of structure during solidification in the next class. To sum up, today we looked at comparison of simple phase diagrams which are calculated theoretically from simple model and experimental diagram. There are some deviation. We learnt about why there is a deviation. We went a little higher order of calculation using regular solution model, which will give better fit. Then we looked at limitation of phase diagram and also looked at effect of non-equilibrium cooling on solidification. Thank you.